So for section 3.3, pre-calculus 30, it's page 126 in your McGraw-Hill Ryerson pre-calculus 12 textbook that we'll be using today. This is the first page that you see, the factor theorem. This is very, very similar to the remainder theorem. We actually use the remainder theorem to create the factor theorem. They're very, very close. The remainder theorem says if we divide a polynomial by x minus a, we can plug a into the polynomial, and the number value that we get when we evaluate that will be the remainder. Okay, so that's very important, the remainder theorem. The factor theorem says this, and it's very simple, and I'll just kind of jet right to it here, that when you divide a polynomial by a binomial in the form of x minus a, then this binomial, x minus a, is a factor if the remainder is 0 when you use the remainder theorem. So x minus a is a factor if and only if p of a equals 0. So if we go back to our notes and I show you this page that we just looked at, okay, if we divide this polynomial by this binomial, you would see here the factor theorem states that this is not a factor, this x plus 2, not a factor because the remainder is not 0 when we divide. And that shouldn't be too hard to understand, because if you look at these 4 questions we're going to answer in this lesson, how are factors and remainders related in regular arithmetic problems? So if you take a number like 12 and you divide it by 3, you get 4, remainder 0. You see that? You get 4 as a quotient and a remainder of 0. What this means, and we understand that 3 times 4 then equals 12. Exactly. That means that 3 and 4 are factors. If I took the same number 12 and divided it by 5, I would get a quotient of 2, but I would have a remainder of 2. That means that 5 times 2 does not equal exactly 12, right? And that means that 5 and 2, that pairing, are not factors of 12. Now, 2 is a factor of 12, but 5 isn't. So we have to do some further investigation, right? So that doesn't mean that both aren't. That means that at least one is not. Okay? So we have to be careful here with this, but generally, how are factors and remainders related? Okay? And you can write down this is what I'll write for an answer for this right here. When a number is divided by a factor, okay, by one of its factors, the remainder is always 0. So that's the answer to question number 1. And we see that in this example. Okay. What does the factor theorem state? Well, when a polynomial is divided by another polynomial and the remainder is 0, then that second polynomial that we did the dividing by is a factor. So let's summarize that. So when a polynomial is divided by a factor, the remainder is always 0. Okay, and that is when you put the a value into the polynomial, 0 will always be the output if that's a factor. Okay. The other thing we're going to do too is, how do we find possible factors? Okay. So how do we do that? Well, we input possible a values for binomials and see if remainder is 0. So how do we find possible factors? Well, what you do is simply test some binomials, test some binomial possible factors by plugging a values into the polynomial and see if you get 0. So we're going to be taking a long polynomial, like maybe x, degree 5 or something, or 4 or 3, and we're going to have to fully factor that. That's the whole point of this lesson, is using the factor theorem to factor a large polynomial. So what we're going to do is we're going to test for possible factors using the factor theorem. So how do we fully factor a polynomial? Well, we need to use factor theorem to find all factors. Along with, when you get down to a trinomial, sometimes you don't have to use the factor theorem. Sometimes you can just factor that by sight. So along with other factoring methods that we've already used. So we're going to use the factor theorem, and yeah, THM is a kind of an abbreviation for theorem, just in case you're wondering. All right, and we may have to use the factor theorem 2 or 3 times, though. And so we'll go through an example here with this, okay? So I've got the factor theorem just kind of stated right here, so I'll bring that up if you're not quite finished those notes yet. This is what it says in your text. And we're going to use the factor theorem to determine all of the factors for a polynomial, okay? So here's an example. So this is what you're going to get. We're going to say you're going to get a question saying, what are all the factors, or fully factor this polynomial? So you have to try and guess what the first factor is. And yes, you have to try and guess. I'll give you some hints on how to start guessing, but you're going to have to try and guess what one simple binomial factor is and test it out. All right? So let's start with x minus 1. Is x minus 1 a factor? And here's our example polynomial. Well, what you do is you plug the a value, which is positive 1, into the polynomial. So you find out what p of 1 is. Okay? And you check that. And so over here on the left, I've kind of already started this, and if you plug 1 in, you get 1 cubed minus 1 squared minus 5 times 1 plus 2. And when we evaluate that, what do we get? 1 minus 1 is 0, and 5 plus 2, negative 3. Right? Well, it looks like I have it down here. So we get negative 3. Okay. What does this tell us? What does the factor theorem tell us about this polynomial and this factor? Is it a factor, or this binomial? Is it a factor? No, it's not. So this is a big no, because this is not what? 0. Everyone understand that? Pretty simple. Okay? If the remainder is 0, then we have a factor. So what about x minus 2? Let's check this one and find out what a is. So a is positive 2. And it looks like I'm testing x plus 2 here. Okay? I'm testing x plus 2 here. Something got erased. So a value is negative 2, and that's what I'm actually putting into the polynomial here. So we'll test p of negative 2 and find out what that is. So what do we have? Well, negative 2 cubed is negative 8. Negative 2 squared is positive 4, so that's going to be negative 8 minus 4. This is going to be a plus 10 and a plus 2. So that's going to be negative 12 here, plus 12. That's going to be 0. So p of negative 2 is 0. So according to the factor theorem, x plus 2 is a factor. Yes, it is. X plus 2 is a factor. Okay? So I'll tell you, I'll give you a hint. I'll give you a hint right now as to which factors you're going to pick to test, because that's really important. And I'll go back to the textbook for that. So in the textbook, on page, what's it going to be? 28? No, page 129 looks like. And if you're missing some notes, if you read a little bit slower or whatever, after this you can fill in your notes, okay? Just leave some space if you need to. But here's a theorem called the integral zero theorem, and this is what it states, okay? You don't have to memorize this, it's pretty intuitive, but the integral zero theorem states that if we have a binomial factor in the form of x minus a for a polynomial, then what you're going to be looking for is you're going to be looking at this a value here. This a value has to be a factor of the constant. It has to be a factor of the constant term in the polynomial. All right, and I'll show you what that means. So the possible factors for this one that we just did, okay, the possible factors, what we do is we look at the constant term right here, and I do x plus 2. That could be a possible factor, which we tested, and it is. It could be x plus 1. It could be x minus 2 or x minus 1. those are the ones you want to test, because positive and negative 2 and positive and negative 1 are factors of 2. Okay? Don't test this one, x minus 3. Don't test that one because 3 is not a factor of 2. So look at the constant and check those binomials first. Got it? Okay. So here's an example, and again, I'll just kind of pause on this screen for a little bit so you can write down these steps and this example. So write down this example, find all factors of this polynomial right here. So this is a long one. Okay? And we have to try and identify some factors using the factor theorem. Then once we find a factor, we're going to want to use synthetic division to actually do the division. And then we're going to take whatever polynomial is left over, and we're going to keep doing that process until we can nail it down to separate factors. So take a moment to jot down this this polynomial here, and then these are the steps we're going to follow. All right, so here are the steps. If we take a long polynomial like this and we want to factor it, notice that you're not given a factor first to divide. So you have to choose one. And step 1 says choose possible factors, and as we just mentioned, the a values of simple binomial factors will have to be factors of this constant right here. So that's why on the side I've already listed x plus 1, x minus 1, x plus 2, x minus 2, x plus 4, x minus 4, okay? And there are others, right? Right? They keep going, 6 and 8 and 12 and all that sort of stuff. So if you have a list, you can just start picking off some of the easy ones, which would be, the 1s and the 2s and the 4s. Those would be easy to pick. So determine the a for the listed factors. So that's pretty easy. A here is negative 1. A for this one is positive 1, and so on, right? So you find the a values, and then you use the factor theorem. And you simply plug in, take whichever one you want, plug in negative 1, let's say, and you plug that into the original polynomial. So if you check the first one and you put a negative 1 in, okay, 4 times negative 1 cubed, minus 7 times negative 1 squared, minus 34 times negative 1 minus 24, okay? So what do we get here? This is going to be a plus 1. This is going to be a minus 4. That's going to be a minus 7. That's going to be, that's 34, so that's plus 34. And then minus 24. So what do we have here? It looks like we have negative 3, negative 7, so that's a negative 10. And that's a negative 34 here when those two are together, and then a plus 34. So this is 0. The remainder is 0. So using the remainder theorem, we've calculated the remainder to be 0. Using the factor theorem now, we have determined that, yes, x plus 1 is a factor. It is for sure. So when we actually do this division, we should get 2 factors, this one and another one as a result, and the remainder should be 0. So step 3, once you've found a factor, once you've found one, perform either synthetic or a long division. You're probably going to want to do synthetic because it's a bit quicker, to find a second factor. And of course, this down here, when you do the synthetic division, this will represent the second factor. Okay? So again, I have done this already beforehand just to kind of quickly walk you through this, but the synthetic division will yield a quotient of x cubed plus 3x squared minus 10x minus 24. Along with this factor, now I have split this big long polynomial into 2 factors now. And notice that the remainder is 0, so that's good. We've done everything correct so far. So at this point, you have 2 factors, but you're not done. There's a good chance that you're going to be able to factor this degree 3 polynomial now. So step 4 is repeat steps 1 to 3 until you determine all of the prime factors, that is, factors like this, that cannot be factored any further. Right? So we keep going in this process. And again, as we continue this, you look at the constant here. Again, it's 24 again, negative 24. So you list all of the possible factors, or you just pick another one and test it. Okay? And so I've done some work here below for step number 4. We have a negative 24, so I've listed some of these factors. You plug in the a values here, and you check the remainders. Okay? So x minus 1 is not a factor of this one here. X plus 1 is not a factor here. X minus 2 is not a factor. Oh, x plus 2, look at this. X plus 2 is a factor of this polynomial now. So you repeat the process and do your synthetic division. And so you keep going, and this is what happens. You get a second, you get a third factor. So we've got the x plus 1 already from before. We've determined this x plus 2, which is right here. And then we have this factor. And that's going to be x squared plus x minus 12. And when you get to this point right here, you don't really have to do steps 1 to 3 again. You could probably just look at this trinomial and say, hey, I know how to factor that by sight. Or you can factor that by decomposition maybe, right? And so this one looks, it's pretty easy. This is just x plus 4 times x minus 3. These are all prime factors now. They cannot be factored down any further. And so this is your final answer for this example. Notice how we've just picked one factor through the factor theorem, then divided, and then focused on the next factor and done the same thing, and you just keep whittling it down. You keep chopping it up until you get to all of the base prime factors. Okay. Any questions about this example or this process or these steps? Okay. So here's the fully factored form. Now I found x plus 1 first, did my dividing, and then factored this trinomial by sight. The question was, does it matter which factor you find first? No, it does not matter which factor you find first. You're going to want to look for the simple binomial ones that have b, this coefficient as a 1. You're going to want to try and look for these ones first. Then when you get down to this, you're probably going to be able to factor by sight or decomposition. But no, it does not matter which factor you identify first, and it doesn't even matter which factor you list, right? In the list of factors at the end, order doesn't matter as long as you have the proper factors. Okay? I'll just show you the assignment up here. So those of you that have worked through this question, you got it right, and you have no questions. Here's your assignment right here from 3.3 right there. You'll want to check your key ideas in your textbook as well, just to check to see if there's anything that you still are unsure of.
This